In elimination reactions, it's important that you are able to identify the alpha carbons from the beta carbons. So the alpha carbon is the carbon that's directly bonded to the leaving group, which is one of the halogens, and the beta carbons are the carbons directly bonded to the alpha carbon. And so now what happens if we have multiple different beta carbons bonded to the alpha carbon? How do we predict what kind of alkene product we can get from that elimination reaction? And so you can have a primary beta carbon bonded to the alpha carbon. You can also have a secondary beta carbon bonded to that alpha carbon. And so according to Zaitsev's rule, you can have a major product and a minor product. So the major product is essentially the more stable alkene. And you learn that the more stable alkene is the more substituted double bond. So remember that a tetrasubstituted alkene is the most stable, followed by trisubstituted, disubstituted, and the monosubstituted is the least stable. And so according to Zaitsev's rule, the major product in beta elimination reaction has the more substituted double bond. So here's an example of an elimination reaction involving two different types of beta carbons. So we have beta 1 and beta 2 carbon atoms. So they're different because this beta carbon right here is a primary carbon bonded to one other carbon atom. And then the beta 1 carbons over here are secondary carbons bonded to two other carbon atoms. And so the alpha carbon is this one right here, which is bonded directly to the leaving group, which is the iodine atom. And so according to Zaitsev's rule, you're going to have multiple different types of alkenes as a product. And so let's say that this strong base here deprotonates the hydrogen, one of the hydrogens in the beta 2 carbon atom. Then what happens is you'll have a double bond between beta 2 and the alpha carbon, which is a double bond shown here. So this is molecule B, one of the possible product of this elimination reaction. However, if the base here, the strong base, deprotonates one of the hydrogens in the beta 1 carbons, then you can have a double bond here between the beta 1 and the alpha carbon, or a double bond between this beta 1 here and the alpha carbon, which would actually be the same molecule. So this is molecule A, which is the result of the protonation of the hydrogen on a beta 1 carbon. And so you can see that you have two different alkenes here, in which one double bond is between the alpha and the beta 1, and then the other double bond will be between alpha and the beta 2. And according to Zaitsev's rule, the more substituted double bond is the major product. It's the more stable alkene. So you can see that beta 1 here is trisubstituted, whereas molecule B here is only disubstituted. And so molecule A is the more stable alkene, which would be the major product of this elimination reaction. A chemical reaction is known to be regioselective when it yields predominantly or exclusively one constitutional isomer when more than one is actually possible. So in this case, E2 reaction is regioselective. So if you have more than one type of beta carbon, you can have multiple different products possible. And so E2 reaction prefers the more stable, more substituted alkene as the major product. So here's an example that illustrates the regioselectivity of E2 reactions. So we have this alkyl halide here, we have the alpha carbon right here at the center, and then we have two different types of beta carbons. So we have beta 1 and beta 2. So let's say that this strong hydroxide ion right here, which is the base, deprotonates the hydrogen of one of these beta 1 carbons. So what you have is the formation of a double bond between the beta 1 and the alpha carbon. So you can see that deprotonation of a beta 1 carbon results in the formation of a disubstituted alkene. However, if the strong base deprotonates a beta 2 carbon, then you have a double bond that forms between the alpha carbon and the beta 2 carbon, as shown here. So you can see that this molecule D here is a tri-substituted alkene, which means that molecule D is going to be the major product and the preferred constitutional isomer. A chemical reaction is known to be stereoselective when it forms predominantly or exclusively one stereoisomer when two or more are actually possible. So the E2 reaction is stereoselective because of the fact that the more stable stereoisomer is formed preferentially. So remember that a trans alkene is more stable compared to a cis alkene because in the cis alkene, there's a lot of steric hindrance here between the two substituents. Compared to a trans alkene, the two substituents are far away from each other as possible. And so it makes trans alkene or a trans isomer more stable because it has less energy compared to a cis alkene, which contains more energy and less stable. So here's an example. Predict the major product in the following E2 reaction. So here we have an alkyl halide. And this halogen right here is bonded directly to this carbon atom, which makes this carbon the alpha carbon. So let's go ahead and label that. This is our alpha carbon. And then we have two carbon atoms bonded to this alpha carbon. So those are our beta carbons. And you can see that these beta carbons here are actually two different beta carbon atoms. This one up top is a tertiary carbon, whereas the one here at the bottom is a secondary carbon atom. And so those are two different beta carbons. So we can just label this one up top beta 2, and then the one here at the bottom beta 1. And you can see that beta 2 carbon here has one hydrogen bonded to it. And the beta 1 carbon contains two hydrogen atoms bonded to it. And so that means that we can have two different products here, two different alkenes. So if the base attacks, let's say, the hydrogen bonded to the beta 2 carbon, so that we would have a double bond between the alpha carbon and the beta 2 carbon. So one of the products would look something like this. So a double bond here. So this is one of the products of this chemical reaction, elimination reaction. And the second one would be a double bond between the alpha carbon and the beta 1 carbon. So you can attack one of the hydrogens here connected to the beta 1 carbon. And so we could have this double bond here at the bottom instead. All right, and so when you compare the two alkenes here, you can see that this, so we can just label this A and we can label this B. You can see that molecule A is more stable because we have a tri-substituted alkene here versus a di-substituted double bond. And so it makes molecule A the major product and molecule B the minor product. And here's practice problem number 12. What alkenes are formed from each alkyl halide by an E2 reaction? Use the side-sev rule to predict the major product. So for the first alkyl halide here, you can see that this is our alpha carbon right here. And then the two carbon atoms bonded to the alpha carbon are the beta carbons. And you can see that these two beta carbon atoms are different. One is a secondary carbon and the other one is a tertiary carbon atom. And so we're going to have two different alkene products here. So one alkene product will have a double bond between the alpha and the beta 2 carbon atom. The other alkene product would have the double bond between the alpha carbon and the beta 1 carbon. So let's go ahead and draw the two possible alkene products here. So the first one is between the alpha and the beta 2 carbon atom. So we have two methyl groups bonded to the beta 2 and then an ethyl group on the alpha. So that's one of the products. And then the other one will be a double bond between alpha and beta 1. So we can call this alpha right here and beta 1. And so we have this product, or this substituent right here, and a methyl group on the beta 1. Alright, so you can see that for the second product here, there's actually a stereoisomer possible. So these two substituents are in trans position, so you can also have a cis stereoisomer. So the other one would be going will be on the same side as the other substituent. So it looks something like this. So that's the other product when it comes to stereochemistry here. So again, this is our alpha right here, and this is beta 1. So of course, this product right here, according to stereoselectivity, the trans isomer will be more stable compared to the cis isomer. So we can just label this cis, we can label this one trans, and then both of these are di-substituted, whereas this one right here is a tri-substituted alkene. And so according to Zaitsev rule, the alkene that's more substituted is the major product. And the reason why is because of its stability. And for the second alkyl here, you can see that this is the alpha carbon right here. So we can go ahead and label this. And we have several different beta carbons. We have this beta carbon right here. We can label this beta 1. We can label this one beta 2, and this third one right here beta 3. So beta 1 here, you can see that this is a primary carbon. Beta 3 is a secondary carbon. And beta 2 is a tertiary carbon atom. And so you would expect the alpha carbon forming a double bond with beta 2 to be the most stable and more substituted. And so as you can see here, we're going to have three different alkenes here. Three different alkene products because of the fact that we have three different beta carbons. And so a double bond can form between the alpha and beta 1. A double bond can form between alpha and beta 2, or between alpha and beta 3, as shown here. So this is our alpha carbon right here in the middle. This is beta 1, or a double bond between alpha and beta 2, or a double bond between alpha and beta 3. And so you can see here that, again, let's label this A, B, and C. So you can see that molecule B here is the major product because it is tetra-substituted. You have 1, 2, 3, 4 substituents bonded to that double bond. So this is tetra-substituted. This one is 1, 2 di-substituted. And here at the bottom, we have tri-substituted. And so the tetra-substituted alkene will be the major product. And then the other two will be minor products. For the third alkyl halide here, we have the alpha carbon and two different beta carbons here. So we have the alpha, and then we have beta 1 and beta 2. So we have two different beta carbons because this beta 1 is primary carbon, the beta 2 is a secondary carbon. And so again, you can have a double bond between the alpha and beta 2, or a double bond between the alpha and beta 1. And so let's go ahead and draw the products here. So the first alkene here up top, again, let's call this molecule A and molecule B. So the first molecule up top is a mono-substituted. And the second one here, molecule B, is di-substituted. So you can see that this molecule B here, is a trans isomer, right? You have one of the substituent on the opposite side of the double bond, and so the other isomer for this one is a cis isomer, and so let's just draw what that looks like. So the double bond is over here, and then the other methyl group would be right up there. So this is the cis isomer. So let's just call this trans right here. And then this next one is cis. It's called cis because the two substituents here are on the same side of the double bond, whereas the trans isomer, the two substituents are on the opposite sides of the double bond. So you have two isomers for the di-substituted alkene, which is the major product. So between trans and cis, trans would be more stable in terms of selectivity. This would be the one that's more the major product. And for the last alkyl halide here, we have the alpha carbon right here. And then we have two beta carbons, call this beta 1 and beta 2. Well, we can't really call this a beta 2 because of the fact that this is a quaternary type of carbon. It has 1, 2, 3, 4 carbon atoms bonded to it, so we can skip that. And so it looks like we only have one beta carbon, so we don't even have to label that beta 1. All right, so this beta carbon has one hydrogen bonded to it, and so in that case it's only going to have one type of alkene produced, and so that's the double bond between the alpha and the beta carbon. And so let's go ahead and draw the alkene here. We have a cyclopentane, and then a double bond here, and then a dimethyl group. So this is the only product of this E2 reaction. The second mechanism in elimination reaction is the E1 mechanism, and it's sort of similar to the SN1 mechanism in such a way that they both exhibit first order kinetics. So that means that they have a rate determining step. So it takes two steps. You have the slow step, which is the rate determining step, and then the fast step. And so because the E1 mechanism has a rate determining step, that means that the reaction rate is only dependent upon the concentration of the alkyl halide and not the concentration of the base, which makes the slow step unimolecular. It's only dependent upon one reactant. And so this also means that there's going to be a carbocation that's going to be generated from the rate determining step. And so we have a reactive intermediate, which is essentially the carbocation. And so the first step is the formation of the reactive intermediate, which is the carbocation, and then the second step is the formation of the pi bond, the double bond. So here's the summary for the E1 mechanism. You can see that the first step is the rate determining step, which is also the slow step. It's a slow step because the sigma bond between the alpha carbon and the leaving group breaks, which results in formation of this reactive intermediate, which is the carbocation. And then the second step is, of course, the formation of the double bond. So the base will attack the beta proton, and then which then results in the formation of that double bond between the beta and the alpha carbon atom. So the major difference between the E2 reaction and the E1 reaction is that the E2 reaction happens in a single step, which is a concerted reaction, whereas the E1 reaction happens in two steps. You have the rate determining step and then the second step. So here's the energy diagram for an E1 reaction. So you can see that the pattern looks very similar to the energy diagram for an SN1 reaction. So they do have some similarities. So for example, the transition state, the first transition state is similar to that for an SN1 reaction, but the second transition state is going to be different. And the reason why is because for an E1 reaction, there's a total of 3 partial bonds involved. So you have the double bond that's being formed here, and then you have the base that's attacking or deprotonating the hydrogen bonded to the beta carbon. And so you have a total of 3 partial bonds here. You have bond that's forming between the base and the hydrogen, and then a bond that's partially broken between the beta carbon and the hydrogen, and then another partial bond that's being formed between the 2 adjacent carbon atoms. And so SN1 and E1 reaction both have 2 activation energies, 2 transition energies, but different second transition structure. The effect of alkyl halide structure on E1 reactions is actually very similar to SN1 reactions. And the reason why is because they share the same exact step, which is the rate determining step. They're both generating a carbocation, a reactive intermediate. And so you want to stabilize that carbocation as much as possible. And so a tertiary alkyl halide will generate a tertiary carbocation, which is more stable compared to a secondary, a primary, or a methyl carbocation. And so the more stable the carbocation is, the higher or the faster the rate of reaction for E1, which is similar to, again, the SN1 reaction. The strength of the base is also important when it comes to elimination reactions. The strength of the base determines whether a reaction follows the E1 or E2 mechanism. Strong bases typically favor E2 reactions, whereas weaker bases favor E1 reactions. When it comes to regioselectivity, Zaitsev's rule also applies to E1 reactions. So E1 reactions are also regioselective, similar to E2 reactions, favoring the formation of the more substituted, more stable alkene. And according to Zaitsev's rule, the reaction will favor the formation of the more substituted, more stable alkene. And so in this case, molecule A will be the major product because it's tri-substituted, compared to molecule B, which is the minor product because it's only di-substituted. So here's a table that summarizes the characteristics of the E1 mechanism. So you can see that the kinetics, the mechanism, identity, and pretty much everything that's written here is very similar to the characteristics of an SN1 mechanism. They both have first order kinetics. They both require 2 steps. There's the rate determining step and the fast step. The identity of alkyl halide is also very similar. More substituted halides react much faster for both E1 and SN1 reactions, in which tertiary alkyl halides react much faster compared to secondary or primary or even methyl halides. The only difference here is that for E1 mechanism, they're favored by weaker bases, whereas for SN1 mechanism, they are favored by weaker nucleophiles, but sometimes a weak nucleophile is the same thing as a weak base. The leaving group is also similar. A better leaving group makes the reaction faster because the bond to the leaving group is partially broken in the rate determining step. And finally, the solvent is also similar. They are both favored by polar protic solvents. And because of these similarities between E1 and SN1 reactions, an elimination reaction undergoing E1 mechanism will have a mixture of E1 and SN1 products. Similarly, a substitution reaction undergoing SN1 mechanism will have a mixture of SN1 and E1 products. And so, because E1 reactions often occur with a competing SN1 reaction, E1 reactions of alkyl halides are a lot less useful compared to E2 reactions. Here's practice problem number 14. What alkenes are formed from each alkyl halide by an E1 reaction? Use the Zaitsev rule to predict the major product. So for the first alkyl halide here, you can see that we have an alpha carbon and then 2 different types of beta carbons. So let's go ahead and label that. So we have an alpha carbon here, and then we have a beta carbons right here. And you can see that these 2 beta carbons over here are similar. We can just call them beta 1, and then the second one here, beta 2. And so because of that, we're going to have two different products, two different alkenes here. So the first one is going to be a double bond between, so here's a double bond, and then one will be going in this direction and the other one in this direction. And so we have a di-substituted alkene here, and then the other one will be a double bond between the alpha and beta 1. So here's the double bond. And so you can see that the second alkene here is tri-substituted, and so because of that we have our major product right here. And for the second alkyl halide here, we have a tertiary carbon atom, and this is going to be the alpha carbon right here. And then you can see that we have beta 1, beta 2 carbon, and beta 3. So this is a beta 3 because this carbon is different from this carbon atom. And so we're going to have three different types of alkene products here. So the first one will be a double bond between the alpha carbon and the beta 1 carbon. And so we have this double bond right here. So that's one of the alkene products. And then the second alkene product will be a double bond between beta 2 and the alpha carbon. So double bond here. All right, and the third alkene will be a double bond between alpha and beta 3 carbon atom. So as you can see here, the third one is tetra-substituted, and so this is going to be our major product here. And here's practice problem number 15. How does each of the following changes affect the rate of an E1 reaction? So the first one here is doubling the concentration of the alkyl halide. So we know that for an E1 reaction, the reaction rate is dependent upon the concentration of the Rx, which is the concentration of the alkyl halide and not the concentration of the base. And so we know that this is a unimolecular reaction. It's only dependent upon one reactant, and so doubling the concentration of the alkyl halide would also double the reaction rate. So for A would also double the reaction rate. And for the second part here, what would happen to the reaction rate if we were to double the concentration of the base? Well, since the reaction rate is not affected by the concentration of the base, then rate is not affected. And for part C, it says changing the halide from a tertiary halide to a primary halide. So you can see that the E1 reaction reacts much faster if we were to use a tertiary halide. And so changing it from a tertiary to a primary would actually slows down the chemical reaction. For part D, it says changing the leaving group from a chloride ion to a bromide ion. So when it comes to leaving group, the weaker the base, the better the leaving group. And so we know that bromide ion is the weaker base compared to the chloride ion. And so changing it from chloride to bromide would actually increase the rate of E1 reaction. And for the last part here, what if we change the solvent from DMSO to methanol, CH3OH? So you know that CH3OH or methanol is a protic solvent, whereas DMSO is an aprotic solvent. And so when it comes to stabilizing the carbocation, we would want something that's capable of hydrogen bonding. And so we want that methanol or something that's capable of hydrogen bonding. And so changing it from aprotic to protic would actually increase the rate of an E1 reaction. And so for part E, this will increase the rate. So here are some of the differences and similarities between SN1 and E1 reactions. They're both similar in such a way that they have the same exact first step, which is basically the rate determining step, the formation of the carbocation. The main difference between them is what happens next, what happens after the rate determining step, what happens to the carbocation. In an SN1 reaction, a nucleophile attacks the carbocation, forming a substitution product. On the other hand, in an E1 reaction, the base removes a proton from one of the beta carbons, which results in the formation of a new pi bond. So here's an example. Draw the SN1 and E1 products formed in the reaction of tert-butyl bromide with water. So the very first step here is to draw the structure of the tert-butyl bromide. So what does the tert-butyl bromide look like? So it has a tertiary carbon atom, and then that tertiary carbon atom is bonded to a bromine atom. So this is a tert-butyl bromide. And the very first step in an SN1 and E1 reaction is the cleavage of this sigma bond between the carbon and the bromine atom. And so what you have is the formation of a carbocation with a trigonal planar geometry. And of course we have a bromide ion here. This is the leaving group. And so again, this is a slow step. This is the rate determining step, right? This is the first step, which is a slow step because this is the rate determining step. So the next step here is different for SN1 and E1 reactions. And so let's look at what happens to the carbocation for an E1 reaction. So for an E1 mechanism, we have the weak base, water right here, which will then deprotonate one of the hydrogens on this beta carbon. So these beta carbons right here are all the same, and so it will deprotonate one of the hydrogens here. So let's say that this is a hydrogen right here. So I'm going to put a hydrogen here, and it will deprotonate this hydrogen, and then what you now have is a double bond. All right, so you will get an alkene here. So that's one of the products of this E1 mechanism. So now what happens to SN1 mechanism? So for a substitution reaction, SN1, again, here's the carbocation right here. And what happens is the nucleophile, so we have the weak nucleophile here, which is the water, will then attack this carbocation right here. And so what we will get is this. So you have a sigma bond between the water, sigma bond between the carbon and the oxygen atom, which generates a positive charge on the oxygen. And so now we'll have another water molecule here, which will then deprotonate. It will deprotonate one of these hydrogen atoms, and then the sigma bond between the hydrogen and the oxygen will break, and then you have a transfer of electrons here. So what we get is an alcohol, a tertiary alcohol. So we got 1, 2, 3, an alcohol, and a byproduct, which is a hydronium ion. All right, so we have this SN1 product right here, and of course the E1 product right over here. And here's another practice problem. Draw both the SN1 and E1 products of each reaction. So for the first one here, we have a tertiary alkyl halide. And so let's concentrate on E1 product first. And so we have an alpha carbon right over here. And then we have two different beta carbons. Here's beta 1 and here's beta 2. So these two beta carbons are the same. Okay, and so that means that we're going to have two different types of E1 products. So I'm just going to separate E1 from SN1 here. And so the first product will be a double bond between alpha and beta 1. So here's the double bond right here. So that's one of the products of E1. And then the other one is a double bond between alpha and beta 2. Alright, so you can see that this product right here is tri-substituted, whereas the first one on the left is only di-substituted. So we know that this is going to be the major product of E1 mechanism. All right, and what about for an SN1 mechanism? So for SN1, the water will basically replace this bromine atom. And so we're going to have an alcohol, a tertiary alcohol. And then the water, one of the water molecules, will deprotonate one of the hydrogen atoms right here, and then the sigma bond breaks, and you have transfer of lone pair of electrons to the oxygen. And so what you now have is an alcohol. So this is the product of an SN1 reaction, and this is the product for the E1 reaction. And for the next reaction here, we have a tertiary alkyl halide reacting with ethanol here, which is a weak base. All right, so we have a tertiary alkyl halide here. So this is our beta or our alpha carbon right here, and we have two different types of beta carbons. So again, these two carbon atoms right here are similar, so they're both beta 1. And so for an E1 mechanism, we're going to have two different types of products. So you can have a double bond between the beta 1 and the alpha carbon. So 1, 2, 3, 1, 2, and 3. So that's one of the products of the E1, and the second product would be a double bond between the alpha and beta 2. So we have a double bond here. All right, so these are the two products of the E1 reaction. And so now what about the SN1? So for an SN1 mechanism, you can see that the oxygen will attack the carbocation. And so what you now have is something like this. So that's 1, 2, and 3, 1, 2, and 3. And then an oxygen right here. And 1, 2, 1, and 2. So these are the potential products of an SN1 and E1 reactions. And so again, for E1 reaction, this is going to be the major product right here, because of the fact that we have a tri-substituted alkene versus a di-substituted right here. So this is going to be the minor product right here. All right.